to understand how the so-called Hubble tension manifests itself, in order to trick cosmologists into believing that it is real, can be done quite simply. But before we begin, let's quickly review what the so-called Hubble tension is meant to be. It arises via the apparent difference between the Hubble constant when measured utilizing cosmic distance ladder techniques, and the value obtained when utilizing the cosmic microwave background radiation, also known as the power spectrum Hubble constant. So then, how can these values be significantly different, when they are meant to be measuring the same thing? Well, the answer to this should be extremely obvious, but apparently, it is not obvious to the cosmological community. The Hubble constant is a measure of the rate at which space-time is expanding. However, the fundamental assumption made within the standard model of cosmology is that space-time is expanding uniformly in all directions. In other words, the Hubble constant is indisputably spatially constant. When one pauses momentarily to consider this assumption, one is left with the extremely obvious conclusion that there is no experimental evidence for the existence of this basic assumption. In fact, this assumption has now become scientific religion. Appearing on screen, you will see a population of galaxies. When we observe a specific celestial object tethered to a galaxy, we measure a certain value of Hubble constant, appearing as H0. We term this as being the astronomical Hubble constant, and it forms the basis for the cosmic distance ladder measurement technique. However, when we observe the cosmic microwave background radiation, we measure the power spectrum Hubble constant. We term this to be the cosmological Hubble constant. At this stage, I will emphasize that this video presentation is a companion publication to the article appearing in the link at the bottom of the screen. Okay, now that we have defined what the problem is, let's explain why the difference in Hubble constant measurements is fictitious, and doesn't actually exist. In other words, let's explain why the so-called Hubble tension doesn't exist. Therefore, the standard model of cosmology is perfectly fine, nothing is broken and nothing requires fixing. To begin explaining the cause of the so-called Hubble tension, we will borrow a concept from sonic black holes, and the famed Canadian physicist, William George Unruh. A lot of public information exists dealing with sonic black holes and Unruh's work, so we'll leave this up to yourself to investigate. However, to cut a long story short, we shall be treating space-time like a fluid in motion. Moreover, rather than space-time flowing into a black hole, we'll consider space-time to be a fluid flowing towards the center of mass of a galaxy. This means that space-time will appear to be flowing faster, the closer an observational target gets to the center of mass of a galaxy. When we add the effects of accelerated cosmological expansion as a consequence of the Big Bang, we end up with a value of cosmic distance ladder Hubble constant, appearing as H0, which is higher than the value of the power spectrum Hubble constant, appearing as H5. Thus, the difference between H0 and H5 is termed the Hubble tension. If you're observant enough, you may have noticed that we started this slide with a blank sheet of paper. This represents our toy universe, which is known as a bare vacuum. That is, nothing exists, not even the quantum vacuum. We then added a straight blue line which denotes the ground state of the quantum vacuum, termed the zero-point field. The zero-point field may be envisioned as raindrops on the surface of a pond. Each ripple represents the creation-annihilation process of a virtual particle pair. This process experimentally manifests as the Casimir effect, and we believe it to be the driving effect underpinning accelerated cosmological expansion. Consequently, we measure the power spectrum Hubble constant, appearing as H5. Then, we added a galaxy in plan view, along with an observation target. This could be a red giant, or Cepheid, or something else which produces light and is suitable. It doesn't actually matter what it is, only that we can observe it and execute the appropriate measurements. From this object, we obtain the cosmic distance ladder Hubble constant, appearing on screen as H0. Hence, this so-called Hubble tension has arisen. Next, we project the galaxy onto the zero-point field in the manner shown, such that it generates a space-time drain into which space-time can flow, ending up in what we term the dark reservoir of quantum potential energy. It should be noted that volumetric projection onto a two-dimensional plane is a common engineering technique, heavily utilized in fluid mechanics, particularly involving aerodynamics and aerospace engineering. Finally, as we can see, the dark reservoir of quantum potential energy is the energy source powering the zero-point field and consequently, the Casimir effect and accelerated cosmological expansion. Hence, the obvious question now is, what about dark energy? Where does it sit in all this? Well, in the context of this specific illustration, dark energy is represented by the sum of effects contained within the brown box, as shown. Let's now summarize what we have learned. The concept of the so-called Hubble tension, which is the apparent difference in the Hubble constant measured using cosmic distance ladder techniques and the cosmic microwave background radiation, is explained in the context of the assumption of uniform space-time expansion in all directions. Our presentation proposes that space-time may be treated as a fluid flowing towards the center of mass of a galaxy, influenced by concepts from sonic black holes and physicist William George Unruh. The accelerated cosmological expansion resulting from the Big Bang, and the flow of space-time towards the center of galaxies, contributes to the observed so-called Hubble tension. The difference between the Hubble constants is a consequence of space-time behaving like a fluid, and ultimately, there is no actual tension, thus, asserting the validity of the standard model of cosmology. In other words, the standard model of cosmology is fine, nothing is broken and nothing needs to be fixed. Lastly, please remember that this video presentation is a companion document to the research article appearing in the link at the bottom of the screen.